also for the opportunity to be one of the speakers for this workshop. Yes, the aim of my talk is to explore the potential role that AI can play in the discovering process in the context of physics. And in particular, uh, I will discuss this possibility from the specific perspective of the particle physics. And what I mean is that we want to see whether the machine would be able to reproduce some of the main aspects of the standard model, starting from the experimental data. And yeah, what I'm going to talk about is mainly based on this work I did in collaboration with Fernando Quevedo and a graduate student, Aya Abdelak from NYU Abu Dhabi. But but then I will also include some improvements of the results that you can find here. Yeah, this is the plan of my talk. I will start with an introduction in which I will explain the main motivations for this kind of research. Then I will I will quickly review the techniques that we need to understand the results. And then I will show you the results. I will start with the classification of the particles in baryons and mesons, what AI can tell us about this kind of classification. Then the main part of the talk will be about the flavor symmetries of the standard model. I will discuss this from different perspectives. And the last part will be about the excitations. So if we are able to classify particles which are excitation of each other. And and then I will conclude. But let me start with the motivations. So, okay, it's clear that we are in the age of AI. This is also part of the title of this workshop. And one of the most fascinating aspects of application of AI in science and in physics in particular is the possibility to have a contribution from AI in the discovery of new physics. And but if this is the aim of the application of AI, then it is important also to establish whether the machine is able to reproduce what we already know about particle physics. In this specific case, I'm talking about the standard model, and in particular, the capability of the standard model in classifying particles according to quantum numbers, like the baryon quantum number, and the conserved charges of the standard model. And actually, there are some results on this line in other fields, like in chemistry, where people have been tried to apply unsupervised machine learning in order to reconstruct the periodic table of the chemistry, starting from experimental data regarding the chemical compounds. And so our idea was to try to do something similar in the context of particle physics. There are other attempts also in particle physics, but most of the approaches are trying to reproduce the expression of the Lagrangian, the gauge structure of the standard model Lagrangian using symbolic regression. But we think that the first step in deriving the standard model is the observation of symmetries and conserved quantities from the experimental data. So yeah, just to be clear, the idea is to provide to the machine just the experimental data and see whether the machine is able to give us theoretical aspects of.
When you say experimental data, you mean from accelerators?
Yes, basically we are going to use experimental data regarding the mass, the lifetime, and the spin of the particles, or the decay modes, the data regarding the decay modes. So yes, from experiments.
But then you're inputting already the types of particles that you have, because another way of saying this is experimental data are just a bunch of, scattering cross sections.
What I mean is that, yes, we are assuming that we know the particles. I mean, we can label the particle with some name, and we say that the particle is that particle with that specific mass, that specific spin and lifetime. And see, the idea is to study the similarities between those particles. That's the idea. Yeah.
Could you put it also in a grand unified theory kind of framework, like give it a group and tell it to start breaking in and match the standard model? As a structure, let's say.
Yes, it depends on how you want to implement that. But are you talking about still using that data, or?
Yeah, I mean, that's right. Yeah, I mean, see what group or what symmetries you could break in order to reproduce the experimental data or the standard model.
Yeah, in principle, yes. I will show you something about flavor group symmetries. But yeah, in principle, one can try to do something similar. I mean, try to explain what we observe in the data, try to extrapolate information about the group symmetry. Yes. But yeah, what we have done in this work is just to rediscover things that we already know. So just from the standard model perspective. So yes. Okay, the methods that I'm going to use are very basic in machine learning. It's just unsupervised machine learning for most of the results I'm going to show you. And I will quickly review these methods, but just to mention them, what I'm going to use is just dimensionality reduction techniques, so both linear and nonlinear ones, and clustering methods. I'm going to review them. Yes, but before doing that, let me just say that if we want to extract theoretical information from the data, we are saying that, okay, we are kind of assuming that in the data, these information are encoded somehow. The important thing is to understand the best way to represent the data in order to see some kind of correlation and similarities which can be interpreted in a physical way. So just for giving you, show you an example, this is a very simple plot of the mass of the particles, the light particles, versus their lifetimes. And we can see just from this plot that we can recognize two clusters in terms of lifetimes. We have here the particles which are lifetimes of order of 10 to the minus 22, 20 seconds. And these are those particles which decay mainly through the strong interaction, so for which the interaction is more likely. And whereas in this other case, we have a cluster for particles with lifetimes of order of, here is 10 to the minus 6, 10 to the minus 7. And this actually interacts mainly through the weak interaction. And so just looking at the lifetime, we can distinguish two different clusters. Then we can also look for outliers in this plot. Here in the middle region, we have at least 3 particles. Here there is pi 0, eta, and sigma 0. And these are particles for which the decay is mediated mainly by the electromagnetic interaction. Here we have the neutron, for which the lifetime is much larger, is order 10 to the 3 seconds. And yeah, but the reason for this is because of the small difference in mass with respect to the proton, which is the main decay channel for the neutron. So then one can also look at the mass of these particles and see that we have a kind of classification of the particles in terms of mass. All the particles with mass equal or larger the neutron mass are baryons in this case. We are considering just the light one, so this is true. Whereas for the all the other parts, for the mesons, the mass is lower. And of course, this is not true anymore when we include also the heavy particles. And so we need to find also a way to classify particles in baryons and mesons. This will be one of the questions I will try to answer. Okay, but in this case, okay, this is just an example, and we can see from here that we can look at the data and try to get interpretation of what we see in these kind of plots. But this is a very simple example because we just have the mass and the lifetime. Then we can ask what happens if we want to consider more complicated data or higher dimensional data sets. This is what will happen if we consider the decay modes I was telling you. In this case, the dimensionality of our data set will be very large, order of 1,000 features for each particle. So we need to figure out how we can we can visualize this kind of data and try to extract information from them. Okay, this is where artificial intelligence can help us, in particular machine learning, because there is a subset of techniques in unsupervised machine learning which are called dimensionality reduction methods, and these actually are trying to reduce the dimensionality of the data in order for us to visualize them. For instance, if we start from a data set with order 100 features, we can reduce the dimensionality of this data to just 2 or 3 in order to plot them and have a visualization of the data. Okay, the idea here is that in the case of the decay products, we would expect to have a lot of physical information encoded in the decay modes of the particles, information like the internal structure of the particles, but also about the conservation of the charges. So we just need to extract the information from this data. Okay, this is a way in which we can do that, because if we want to use machine learning for extract information, we also need to figure out how we can provide this data to the machine in a way that the machine is able to manage this data. And this is a way in which we can do that in the case of the decay modes. So we can construct a matrix of this type in which we have particles as rows and particles as columns. And for each particle in the rows, we can look at the corresponding decay channels and the decay modes inside the single decay channel. So in this case, for example, we have the pions, which is decaying in muon and neutrinos. And so the idea is to put 1 or 0 to the corresponding column, to the corresponding particle column. So here we have the pion, we will put 1 for the muon, 0 for the neutrino, and all the other entries will be zeros. Okay, the problem here, yes?
But muons and neutrinos and photons are already in the standard model, right? I mean, you're trying to only rediscover the quark side, I guess. Or
here we are just rediscovering, yes. We are putting the information about that particle in this matrix in order to provide it to the machine.
I think so. The question is, you're not trying to discover new particles.
We are not trying to discover new particles. We are trying to discover
symmetries.
the similarity between the particles.
Okay.
Yeah. So okay, we can construct a matrix of this type. The problem here is that we will end up with a matrix where most of the entries will be 0. Of course, we also need to normalize this matrix in order to not give more importance to those particles which have more decay channels. So at some point, one will also need to normalize these entries. But in any case, most of them will be 0. So there will be a lot of redundancies in the features of each particle. So it is important to reduce the dimensionality and so the number of relevant features in order to analyze them.
So you'll have a row for every decay channel, not a row for that particle with all possible decay channels.
In this case, we have a row for each particle, and then I'm going to represent each possible decay mode as a column. So not the decay channel, which is made by more, for example, in the case of the pions, we have muon and neutrino. I'm going to separate those two decay modes.
But it can decay, you have other decay channels.
Yes.
So how do I represent those?
It has more decay channels. We have to go through all the decay channel of the pion. And we will put one for each possible decay mode that we have in each possible decay channel.
Okay, so each row is all possible decay channels for that particle.
You can look at, okay, the idea in which I'm looking at is the opposite in the sense that the row is the particle, so the pi plus, and the columns are the possible decay channels.
So we'll have other ones.
Yeah.
For the other
In the
decay.
case of pion, we have all ones for each decay, for each possible decay modes. So in the case of pi plus, we have muon, neutrino. We can have also other channels, and we will put one for the other as well.
Can this matrix discriminate how many particles are in the final state? I mean, for instance, the I0 can decay in 2 photons, but you have a 1.
Yeah, no, there is no information about how many times we can see the same particle in the decay channel. It will be just one.
It can be improved, or
It can be improved, but okay, it depends on the problem that you are studying. In our case, it would not affect the analysis.
okay.
And in any case, there is the problem of, as I was saying, of normalizing the row. So it depends. If we are interested in getting information about, I don't know, the charge conservation, in that case, it would be important also to study how many times. Yeah, that's true. And of course, according to the problem that we are studying, that could be an important issue, or maybe it doesn't affect the problem. In our case, it didn't, at least for the result that I'm going to show. Okay. So yes, let me just quickly review the unsupervised machine learning methods for reducing the data dimensionality. Okay, maybe the most common is the so-called principal component analysis. This is just a statistical method, and the idea is to reduce the dimensionality by considering linear combinations of our features in order to get eigenvectors of the covariance matrix. And once we get the eigenvectors, we can look at the eigenvalues and consider just those eigenvectors which corresponds to the highest values in the eigenvalues. So the idea in this case is to to focus the attention only on those combinations which encode the most of the variance of our data set.
Sorry, the X is the previous matrix or no? I mean, I'm getting lost. So the previous slide had a big matrix.
Exactly. Yeah, X is
channels of decay.
Yes.
And this is the X?
The X, in this case, X is the data corresponding to the feature, so to each possible decay mode in the matrix, the column in the decay in the matrix. So yes, you can think of it like this matrix. And we want to reduce the dimensionality, so we consider a linear combination of the features. The features here are the decay modes. So we consider a linear combination of these features in order to get the eigenvectors of the covariance matrix.
But this is just incidence about these equations, these kind of particle chemistry, quite right? I mean, so the entries of X are they just zeros and ones?
Normalized version of 0 and 1s. And yes, and then we look for the covariance matrix for this data set, and we solve the eigenvalue problem, basically. This is the idea. So once we get the eigenvectors, we can just focus on the most important one in terms of eigenvalues, and then project our data on these eigenvectors. What we get in this way is a reduction in the dimensionality, in the sense that we just ignore all the other eigenvectors, all the other, because they will not afford so much information, so we are allowed to ignore them. The problem with this approach is that it will give us only information about the global variance of the dataset, but in principle we are also interested in the local similarities between among the points, and in order to preserve also the local information, we can consider nonlinear methods. In our case, we consider the t-distributed stochastic neighbor banding. This is nonlinear in the sense that we are interested in looking at the probability of 2 points to be close in the higher dimensional space, so the original space, and we want to preserve this probability. So we define a probability in terms of this Gaussian function, and we consider the corresponding join distribution just by symmetrizing the probability. Then we consider the low dimensional bending. We will have new coordinates here. I'm calling them like yi here. And we want to construct a joint distribution also for this low dimensional representation. In principle, we can use the same expression that we used here, but the problem is that when we compress the data, we have the tendency of points that are far in the higher dimensional representation to be closer than they should be in the lower dimensional embedding. So instead of considering a Gaussian distribution here, we should consider a student t-distribution, because in this case, the heavier tails will keep well-separated points that are far apart in the higher dimensional bending. And so once we have distribution for the higher dimensional space and the lower dimensional representation, we can just ask the machine to keep to preserve the local aspects of the higher representation just by computing the divergence between these two distributions and trying to minimize that. In this way, we are also able to preserve local similarity. Okay, these are the methods that we can use in order to reduce the dimensionality of the data set. But then we want the machine to recognize the similarities by itself. So the dimensionality reduction techniques are useful for the visualization part, but then we want also to see if the machine is able to recognize the similarities. And this can be done using the clustering methods. Yeah, the most used one is k-means. Here, in this case, it is based on this algorithm. So basically, we consider our data distribution. We consider random points in the data space, and we define this distance between the points. We start from random points, which will be the centers of our clusters, the so-called centroids, and then we assign each particle to the nearest cluster center. We compute again the centers of these clusters, and then we repeat the algorithm until convergence. So in this way, we would expect to have at the end that each particle will be assigned to a cluster, and we can also measure how well the cluster is in giving a cluster for each particle. This can be done by defining some kind of score. We can do something like this in terms of intra-cluster distance and smallest mean distance.
Is this clustering distance, does it depend on the energies we make the measurements, or this is constant, right? That's absolute.
Energy, no. This is just statistical consideration. There is no physics in here. And of course, if you have the distance that you see in the points will depend also on the physics, in the sense that we are trying to look at the similarity between the points, the statistical similarity, and this similarity will be due to physical. This is the physics that we want to extract.
That's right, like the picture you showed us at the beginning with the particles. Is that picture, does it change, or these are fixed points, any energy, or?
The picture, you mean
this one, yeah.
Okay, yeah, in this case we are considering the mass, so
it's all fixed, and the lifetimes are all...
Yeah, these are fixed quantities.
But it's not at a certain energy, right? A scale, or that don't depend
on... what do you mean exactly?
Like, this experiment has been performed with a certain energy scale, so that you measure a certain mass and a certain lifetime.
That's right.
If you change the energy, you might see some variation. It might be good to compare how these vary. I mean, you can do statistical analysis in a sense.
Yes. I mean, to see how it changes with the energy.
That might give you both clusters better together. So just to help another parameter to help both clusters together or not. But yeah, that's just.
Yes, for sure, it's something that. Okay, yes, but so this is a way for getting clusters using unsupervised machine learning. An alternative way would be the so-called hierarchical clustering, because the problem here is that we need to specify the number of clusters that we want. This is done by choosing the number of initial cluster centers, and we can solve this issue by these other methods. The algorithm is similar in the sense that it's using some distance again to measure the distance between the points. But the difference here is that we do not fix the number of cluster centers. We just started from the each particle, which is a point in this case, and each particle will be its own cluster, and then we will use the same algorithm to put particles in the same cluster. So we will have different levels and at each step of the iteration, and at each step we will have a number of clusters which is changing. At the end we will just have one big cluster which is including all the particles. So yeah, the advantage here is that we do not need to specify the number of clusters, but we see how it's changing at each iteration. Okay, these are the methods that I need to use for showing you the results. And let me just show you what happens in the case of the data regarding the matrix that I was showing you before. We will have this problem here. Now we know how to solve it, because we can just apply principal component dimensionality reduction. So we can reduce the dimensionality to be just 2. So I will just consider the first 2 components. This is and just project the data on these 2 components. This is the plot that we have. Here, the color is for the baryon number, and the absolute value of the baryon number. And we see that we do not get two different clusters, but at least we have a separation of the baryons from the mesons. Yeah, we have the mesons in the upper part of the plot and the baryons in the lower part. So if you want, this is a generalization of the classification I was showing you in terms of the mass. In this way, this is a way in which we can work also for heavy particles. So at least we are able to classify the particles according to these principal components. It works.
Can you remind us what's the principal component again? 2 and 1?
Yes.
Sorry for that.
No. Here, I'm considering the projection along the principal components, which are just the eigenvectors of the covariance matrix. So the first two principal components are the components which corresponds to the two eigenvalues. To the highest eigenvalues, and this will encode the most of the variance of our data set. And so these are the principal components, just the eigenvectors of the covariance matrix. And okay, you can see that it's working very well for all the particles except for two red dots here. And these are the points that corresponds to the neutron and the proton. And actually it makes sense because we are just considering the decay modes. And okay, for the proton, of course, this analysis will not work. Okay, then we can also do something different. Instead of considering just the first decay channel, we can consider also the decay channels of the decay modes of one particles. So in this case, we will have the full chain of the decay. And if we do the same analysis in this case, this is the plot that we would get. In this case, I'm including in the color also, okay, it's not just the absolute value, it's the baryon number. So we will have -1 for the antibaryons, 0 for the mesons, and +1 for the baryons. And we do see here that we actually get cluster in the sense that we see this split. And so in this case, we are able to separate the baryons from the mesons from the antibaryons. So we are able to put a quantum number with its sign for each particle. And okay, the plot on the right is just for a zoom in the dense region, just to show you that the separation is still true in this this central region.
Sorry, I'm confused.
Yes.
So are you assuming you know the baryon number, or?
I'm not assuming that I know. I'm just using the color here to see, to let you.
Just identifying some clusters, I guess.
Yeah, exactly. To let you, because as I told you, the idea is to visualize the data and then to try to. Yeah, to try to see if from the data we have the cluster that we see are what we would expect to see.
So the data, I should think, is just a bunch of black dots.
Yes. Yeah. Exactly.
And then you ran the algorithm to convergence, and it separated it.
Exactly. The algorithm split the dots, the black dots, and then I'm putting the color just to show you that those split corresponds to the values in the baryon number. Okay. And of course, if you want, this is what we get when we want to visualize the data. But then we can also use, as I told you, the clustering methods. And in that case, the machine will give a label corresponding to a cluster. So the color will be the label, or the label that the machine is giving to the cluster. And then we can see that the label corresponds to the baryon number. So we do get different labels corresponding to different values in the baryon number.
Could you really say that it's plus and minus 1, or should it just be
no, just 3 different families. We cannot say that they are plus or minus 1. Yes. Okay, so these are the results that we can get when we consider the data regarding the decay mode. Then we can also consider a generalization of the plot that I was showing you at the beginning. So in that case, we were considering mass and lifetime. We can include also the spin into the analysis. In this case, we will have three features. Again, the spin is something that can be measured, so we can give it to the machine as input. And in this case, it doesn't make sense to consider the principal component analysis because the dimensionality is already low in this case, it's plus three features. But it makes sense to consider the non-linear relations between these three variables. So I'm going to use the t-distributed methods I was explaining you. And if we do this, then one can consider to reconstruct the historical path in the particle discovery. So we can start just with the lightest particles, and this is the plot. Here, again, I'm showing you the first two components in the nonlinear dimensionality reduction. And okay, if we look for the proton, we see that the proton is in the same cluster of the neutron. So even though we have a limited number of particles, we do see cluster even here. And for example, we have the pions which are close, and the same is true for the rho, the deltas. So basically what we are getting here are clusters corresponding to the isospin, iso2 multiplets. Okay, in principle I could say that these are just clusters corresponding to the spin, because these are, they have different spins. But actually this is not true. Here I'm also including the leptons, muon and positron and electron. And they are not clustered together with the proton and neutron. So the machine is also putting inside the information about the mass. So it's a non-trivial clustering here.
So
yeah.
So it's telling you, so can you go back one slide? So this clustering is telling you that you have these three types of particles, and within each cluster it's saying that particles of that type primarily decay to other particles of the same type. Is that what the...
Yeah, exactly, yeah. I mean, the machine is looking at the similarity between the data that we have in the matrix, and yeah, it's looking at the fact that there are particles which share some decay channels, let's say.
So it's hinting at a conserved quantity.
Exactly, yeah.
Okay. And then for the SU2 case, I mean, how do you...
Here I'm considering not the decay modes, mass, lifetime, and spin.
Okay.
The data regarding these three particle properties.
But can you really get SU2 from this?
Like,
but this is very similar to what people did in the 50s, right? I think the 60s. In this step.
Yes. And I'm just reproducing things, yeah.
So they're just, now it's just clustering because they all have the same spin.
Isospin.
But yeah, exactly. But the isospin is not something that can be measured. So yeah, exactly. The idea is to reproduce what has been done in the past. Exactly. Yeah.
Sorry, why can't you do PCA here?
Sorry?
Why can't you use PCA? Why must you use TSNE here?
In this case, I use TSNE just because I was telling you that we just have three features. So we don't need to just reduce the dimensionality. We also need to look at the nonlinear relation between these three features.
Have you tried PCA or it doesn't work?
Yeah, we tried with PCA, but of course, in the case of PCA, most of the variance would be the spin, because that is the feature that is giving us the variance in the data set. Yeah.
I'm not sure how you're dealing with antiparticles, because, for example, you have electron-positron, but you don't have proton-antiproton. And sometimes in isospin multiplet, you have particle and antiparticle. So,
yeah, no, in this case, it's not important of, there is no importance about the anti-partners. Because we are talking about spin, mass, and lifetime.
But then why do you put mu plus, mu minus? I mean, then they should be the same, right?
Yeah, they are the same. Yes, they are the same. They are the same.
So I should see only one point there.
Exactly. This is the same point for both.
But 2 for the toe, which is also left. You have 2 points for the toes.
Yes, in the case of the taus, yeah, the taus, in this case, they are different because
They also left ones a bit like electron.
in terms of spin, mass, and lifetime, that turns out to be in the same point. There is no distinction between them.
Then let's see, you have the pions, pi plus, pi minus, they should be in the same place.
That's true. They are.
That's true, they are.
Yeah.
But what about the rows?
The rows, they are all 3 different. Yeah. Yeah, this is just from the data.
At the point of these clusters, those tell me the multiplets. So I would have like 3 states.
Exactly, yes. And indeed, I will, I will use this information later. Okay, this is, as I told you, we can try to start with the lightest particles, then we can also include the particles that we know are made by at least one strange quark, and do the same analysis again. And this is the result that we get. So if we look at the proton and neutron again, they are still close to each other, but then they are also included in a larger cluster in which we also have lambda, sigma, and psi particles. If we look at the pions, they again are in the same cluster, but also close to the counts eta and eta prime. So basically what we are getting here are the multiplets corresponding to the baryon octet, in this case, of SU3. The 0 minus meson nonet, in this case. And actually the same is true also for the other particles. Here the rho are in the same cluster with the other counts of the spin parity 1 minus baryon, meson octet, and here we have the baryon decuplet. So basically we are reconstructing here using this dimensionality reduction the cluster corresponding to the SU3 representations. And okay, I want to stress here again that this is what we get from the dimensionality reduction. Then we can also use the clustering methods. For instance, we can use k-means and specify at least 5 clusters. And the label that we would get are actually the color corresponding to the different representations. Okay, I also included the leptons here, and the cluster does work for the light ones, but it doesn't work for the muon and the taus. And yeah, this is because of the mass information. I mean, because of the hierarchy in the mass, the machine is not able to put them in the same cluster. Okay.
Oh, I'm sorry. Just,
yeah.
But what's the difference from the previous slide?
I'm including more particles here.
Ah, okay, I see.
Here are just the, okay, what we know are made by up and down quarks.
I see.
Here I'm including also the heavy ones. And
but it's exactly the same technique, right?
But the same, exactly.
It's like that. Here you have 1 point for the 2 toes. Or no, is it? Yeah, and in the previous slide there were 2 points.
Yeah, because once we include more particles, of course, it will change also the clustering that we have in the
okay, the symbol.
But yeah, what I want, but the fact that they are distinct here, it means that they have different data about the lifetime. And yeah, once we include more particles, of course, particles that were less similarity before now are more similar. So they were put together. Yeah.
So, has the machine done anything that a human couldn't do just by staring at the data? I mean, if you plot it this way.
Sorry, in which way?
So if somebody just stared at the data or just wrote down this matrix that you had and grinded through the calculation, did the machine just do it faster? I mean, like, what was the advantage of the machine? People did this like in the 50s and 60s. So.
Yeah, they did it, but of course, then for doing this, they needed to develop some group theory considerations, right? Here, the machine doesn't know anything about group theory.
You're just clustering.
Yeah.
Stuff.
Sorry, I had a question about that as well. So far as I can see, you took the data and applied some standard data science techniques, right? It's not really machine learning in any sense, right?
Actually, I'm telling you that the clustering methods are machine learning methods, in the sense that
people could have done it with the same programs before machine learning. K-clustering algorithms, all these different principal component analysis, these are all older than machine learning, right? You could have applied it to the same data.
Indeed, I'm using here unsupervised machine learning. So I'm not, if you are talking about machine learning in terms of neural network and learning process through the neural network, it's not what I'm using here. Here I'm using computer unsupervised machine learning. So I'm not giving anything for the machine to any reference for the machine to learn.
Sure, but it's supposed to cluster, for example, right?
Yes, and this is why I'm saying that the labels here are the labels that the machine is giving to the cluster.
I'm sorry, I'm being very slow about this, but
No.
there are algorithms that do this kind of thing, right? Long people used such algorithms long before machine learning, clustering algorithms. Right?
Yeah, and they are right now considered unsupervised machine learning.
It's just a renaming of the old.
Yeah, exactly. Yeah.
Okay, no, that's fine.
Yeah.
You tried something like autoencoder, which is still unsupervised, and it would be more neural network-based machine learning.
Yes, and we tried with the autoencoder, and it gives the same results. Yeah. Autoencoder will be a more, let's say, machine learning oriented methods. Yeah. And do you have a question?
No.
And
So the real hope would be like, I have new data, and I do this, and I see clusters, and that'll tell me something like I have a multiplet of a certain dimensionality, and then I can work out, say, some group theory.
Yes, of course. Once we have more data in which, I mean, at that time, the idea is that if we have more data in which we have new physics, the machine will be able to highlight the difference with respect to this either.
In fact, it would be even more interesting if you could dig out even the particles from the data instead of telling the machine that there are such and such particles.
Yeah, this
actually
is
seeing them from the scattering cross sections that there may be a peak there that somebody has missed, and the machine calls it a particle and then tries to fit it into this thing. This is
exactly. Like it was be done with omega particles. I mean, the existence of the omega particles was because of this 8-fold way, right?
No, but it's not from the data, right? I mean, I'm saying that suppose that
exactly,
some new particle that came out of LHC, but it's too much buried in the data that.
Yeah, we can say that we would expect to have a particle with those properties, and maybe it turns out to be expected from this kind of data analysis, and we can say that from the data side, we would expect to have a new particles that has not been discovered yet. Yeah.
But the setup here is like imagining the LHC, so you know what particles you're shooting in, you know what particles you can observe. And at the moment, you're just asking about quantum numbers.
Exactly, yeah.
Yeah, so and this came up before, right? You're not looking at like a peak as a function of energy or something, which would tell you that you have a new particle. But looking at the quantum numbers, you could see maybe there's a new particle with some charge or something.
You try like inputting like particles with like representation random like SUN whatever and see whether you can have like a SO10 or SU5 clustering in some sense.
No, we didn't try, but which way are you suggesting?
So like just give it some particles that is already like symmetrically broken to like lowest symmetry group, and then you kind of like unsupervise and look at the latent space. Maybe there's SU5 or SO10 or like stuff there, because they're doing something similar here, but more from meson and baryon to SU3 representation.
We didn't try this. I mean, using some supervised methods, we have been trying to. Okay, I will tell you after that what we have been trying to do, but not in terms of higher group structures. We didn't try that. Okay, so yes, this is what. Okay, the labels that we have here are the labels that we would get from K-means approach. Then I was telling you that there is this other alternative, which is hierarchical clustering. In this case, if you remember the algorithm, we start with as many clusters as many particles. So each particle is its own cluster. This is the zero level in the hierarchy. Then we will end up with just a single clusters at the end, in which we have all the particles together. So the first non-trivial cluster here is the ones corresponding to the yellow clustering, and these are actually the clustering. These are actually the clusters corresponding to the SU2 isospin symmetries that I was showing you before. And the second non-trivial one is the ones corresponding to the SU3 multiple representations. So yeah, the advantage here is that from just one type of clustering, we are able to get both. So we are able to see also in the substructures inside the SU3 clusters, for example.
I'm sorry, what do you mean by the first non-trivial clustering? I mean, for any K, it gives you the clusters, right?
This is, in this case, for this method, we start from each particle to be just a cluster.
Oh, yeah, I understand.
Yeah, so this is, in this sense, is trivial because.
But then the next clustering is for K equals 2, K equals 3, K equals 4, and so on?
Exactly. Yeah, according to that iteration, we put together the particles which are closest to each other.
That's right. So whatever K it gives you, it always clusters, right?
Exactly.
So when you say the first non-trivial clustering, what do you mean by that?
The first non-trivial, I mean the first one. Because the first is, the zero level is trivial, because we have, okay.
You mean K equals 2 then?
K equals 1 in this case, yes.
But the non-trivial one is?
Non-trivial.
K equals 2 or K?
K equals 1, and putting K equals is just a notation. K equals 0 to be the zero,
okay, no, to be
zero
no
iteration.
Okay, no, I understand. Yeah, that's fine.
And so yeah, in this sense. And of course, one can also see which one is the best cluster, in the sense, the best level of clustering, looking at the score I was mentioning you before, which one has the best cluster score. Okay, then the natural next step is to include also particles which are made by charm and bottom quarks. In the case of the charm particles, we would expect to get multiplets according to the SO4 group symmetry. And so in the case of the baryons, we would expect to get a cluster made by at least 20 particles according to the multiplet representation. In the case of the mesons, we would expect to get at least 15, a cluster made by 15 particles. So yeah, we basically have a generalization of the eightfold way, in the sense that we would expect to get cluster according to these structures, in which the first layer is the ones corresponding to the usual SU3, and then the other layers corresponds to a non-vanishing value in the charm quantum number. And so, yeah, we can include these particles and try to do the same. But, okay, if we look again at the proton and neutron, we see that they are still in the same clusters as before, because the charmed counterpart of that group multiplet is here, so it's not, of course, they are not in the same cluster. But again, yeah, the explanation for this is the fact that we are giving also information about the mass of the particles. So somehow, and this is also expected because the SU4 symmetry is not a good symmetry of the standard model, in the sense that we have the mass of the charm quark, which is closer to the QCD scale. So it's a broken symmetry, and this is what the machine is. This is why we do not get the same cluster for the particles. But even though we do not get cluster according to the SU4 multiplets, we see that all the particles made by a charm quark are together in the same cluster. And the same is true for the bottom particles. So what we are getting here are not clusters according to SU4, but clusters according to the charm and the bottom quantum numbers. Okay, so yeah, just to summarize, we are able to get information about the SU3 representation, the SU2 isospin representation, the strange, the bottom, and the charm quantum numbers. Then, of course, there is a problem here, because when I say that these are the clusters corresponding to the SU3 multiplets, I'm just kind of assuming that I know that these are the cluster corresponding to that symmetry group. Because what I'm seeing here is just that they are clusters, so we see that there is some kind of symmetry which is responsible for these similarities between the particles, but I do not know which symmetry it is. So there are some ideas in the literature. There is this work by the next speaker, by Sven, in which they have been tried to propose an algorithm for the symmetry detection, identification of the symmetry. Because from the clustering, we can just say that there is a symmetry, but we want to know exactly which kind of symmetry it is. And for doing this, we can, in this case, introduce a supervised machine learning in order to learn the symmetry in terms of generators of the symmetry group. This is something that can be done in our case. And for instance, as we were saying, we have, from the size of the cluster, we can assign also the isospin. Because in the case of the SU2 representation, we know that in the cluster of proton and neutron, we just have 2 particles. In the case of the pions, we have 3 particles. So we can actually assign the isospin states for those particles, and then look at the transition between these 2 states, and we can ask the machine to identify, let's say in this case, the ladder operator, which allows us to go from one state to the other one. And this is something that the machine can learn in the case of SU2 symmetry. And then we can consider this combination in order to get the generators. And these are the results. So at least apart from the normalization, we would get, in the case of isospin 1/2, we do get the Pauli matrices. And also for spin 1, we get the expected matrices, for at least for the first 2 generators. The third one is automatic. And we can also check that the algebra is the one expected. So yeah, this is a way of learning the symmetry starting from the generators.
Oh, sorry, what do you mean by generators then?
The generators of the algebra. For the symmetry, when the generators of the symmetry group.
Sure.
So in the case of SU2, we would expect to have apart from 1/2 factor, we would expect to have the Pauli matrices, right?
So in the clustering, it counts the number of points and then creates some symmetry between them and creates some generators.
We count the numbers of points for establish the isospin, the value in the isospin.
So don't the clusters tell you the dimension of some representation?
Exactly. Yeah.
So that's what the information you're starting with.
Yeah.
Do you assume it's SUN or?
I get from the size of the cluster in terms of number of points that we have in the cluster, we are able to extract information about the dimensionality of the representation. Then we want to see
How do you go from that to the whole group?
in terms of generators.
Okay.
And this is something that can be learned by, okay, in the case of isospin, we consider the ladder operator T plus and T minus, looking at, because when we know the isospin, we can assign an isospin state to each particle, 1, 0, 0, 1 for the proton and neutron. And then we look at the transition between one state to another state. And we ask the machine to learn the matrix which is able to, which allows us to go from one state to the other one. So we are learning here the ladder operator T plus and T minus. And then we construct the two generators in terms of, the first two generators in terms of this combination.
So, for example, can you tell, so you have a cluster made by 8 particles, so you're saying that you can tell that it's a representation of SU3 and not of SU2, for example? It's not like the
in the case of SU2,
7.5 spin.
In the case of SU2, yes, it does work, and we can say this is because we get the generators which close the algebra that we would expect.
No, I know, but
yeah.
suppose I didn't know. Suppose I see a bunch of particles made by 8 states, right? This could be the 8 of SU2 or SU3, but it could also be the 8 of SU2, right?
Exactly. Yeah.
And you say that you can tell which one it is without any input. So I'm basically looking at all at the data. It's telling me that it's a representation of the generators are those of SU3 and not of SU2.
Yes. In the case of the pions, yes, because we do get these generators, which could be also. I mean, it's a 3-dimensional representation. So in principle, could be also for SU3. But we are able in this case to say, no, these are the generators that we would expect for SU2.
And not the fundamental of SU3.
Exactly. And so at least for the SU2 part, we are able to get the generator. And we can say that these are the generators of SU2. Okay, just the last part is about the excitations, because so far the results were, I showed you, were for the particles with different quark structures. Then we want to see if the machine can say something about similarities among particles which have the same quark structures. So particles which are excitation of the same ground state. And so we could do a similar analysis. In this case, we just focused on the baryon case, because also from the experimental point of view, the situation is more clear in terms of excitations. So we can consider all the excitation of the ground state for the delta, the lambda, the neutron, the sigma, and the psi particles, and do the same analysis. So again, applying the nonlinear dimensionality reduction in the case of the decay modes again. And this is the clusters that we get. I would say that we do get just 3 different clusters clearly separated, and these are the ones corresponding to the sigma, the lambda, and the psi particles. Whereas in the case of the deltas and the nucleons particles, we do get 2 clusters, but the main problem is that these 2 types of particles share the same clusters. And again, actually this is not wrong in the sense that at the end of the day, the delta particles have the same quark structures of the nucleons. So they can be interpreted as the excitation of neutron and proton. And for this kind of analysis, the main reason is that they share the same main decay channels, which is just a nucleon, the neutron plus the pion. So, so it's somehow expected to have the same cluster for them. And then we also have outliers in this case, and we have these isolated points, 3 points, and this corresponds actually to the ground states. Because if we look at the decay modes for the excitations, I mean, the similarity between them is due to the fact that they share the same ground state. But of course, this reasoning doesn't work for the ground states, for the ground state itself. Okay, yeah, the idea is that we do get the cluster here. The machine doesn't know about the excitation relationships between them. So we can just, we have the clusters, we can just try to plot them in a plot of the total angular momentum versus the mass. And if we do something like that, we are able to recognize the so-called Reg trajectories. So the linear relation between the total angular momentum and the mass squared. And we also are able to see the fact that this trajectory have similar coefficients in the linear term. And so we are able somehow to observe what we know about the Reg theory, which means the universality behavior in the alpha prime parameter. Okay, I don't have time to say more about this, but yeah, just to conclude, what I wanted to show you is that by applying unsupervised machine learning, we are able to get information about many aspects of the standard model. If we apply the analysis to the decay modes, we are able to reconstruct the classification in terms of baryon number. And if we consider the spin, the mass, and the lifetime, we get cluster according to the SU2, SU3 representations, and also information about the strange, the charm, and the bottom quantum numbers. I mean, we do get cluster according to the different values of these quantum numbers. And if we consider excitation, we're able to reconstruct the Reg trajectories, so the relationships between the excitation with the ground state. And of course, this is just for rediscovering what we already know. The idea is that this can be extended to maybe get some insight for beyond standard model candidates, as you were suggesting as well. And maybe also going inside the structure of the particles, like looking for the quarks and just from the data. Okay, yeah, I stop here and thank you for the time.
It seems your method depends, if you add more particles, the grouping changes.
Exactly, yeah.
Is it possible that you can predict what particles you will need in order to make the grouping perfect or better?
Yeah, this is a way, and actually it's very true what you said, because if we consider all the particles that we know and we do the analysis, it doesn't work. I mean, in the sense that we do not get the results that we got. So yes, I think that if we expect something, we can say that we will need this particle with this specific, I don't know, in the case of the mass, spin, and lifetime, with these specific values for these three properties in order to have a group which provides what we would expect if there is some symmetry group that we would expect to have, yes.
So that's a prediction.
Exactly,
Like,
yeah,
which is
that would,
quite interesting.
yeah, I agree, yeah.
Any final questions? If not, let's thank Pellegrino again.